Okay, I think we've worked on some issues, and we're going to start on review for Module 11. We only have 3 left that we didn't do last week. So number 8 says if it's maker using water and a solute that dissolves endothermically with a beaker or cold. An endothermic process takes in energy and it feels cold. So that would as a side note, an exothermic process gives off energy to the systems. Number 8 would be it would feel cold. An endothermic process feels cold. I'll show you one in class 8, which I will be on the 24th. It says, what is the difference between molarity? We know the similarity between them is that they're both concentration units. Molality is moles of solute per liters of that's really wrong. Molality is moles of solute per kilograms of solvent, and molarity is moles of solute per liters of total solution. So that's the difference. And we've talked endlessly about how you make both of the types of solutions. If you want to protect water from freezing, you best accomplish it, and your choices are sodium nitrate, magnesium nitrate, and aluminum nitrate. The way that you determine which one will protect from freezing the best is you just use the biggest I, or the one that splits to the largest ions when it dissolves. So sodium nitrate is going to split 2 ions, the sodium 1 plus cation and a nitrate anion. Magnesium nitrate would be Mg2 plus cation and 2 nitrate ions. And aluminum nitrate would be an Al3 plus and 3 nitrate ions. So nitrate has an I of 2, magnesium nitrate has an I of 3, aluminum nitrate has an I of 4. You pick the biggest I to get the most freezing. So aluminum nitrate will press the freeze the most because its I is the biggest. These problems, we'll start with number 3. The following reaction is performed in the lab, and I don't have enough chalkboard space to get on one line, so we're just going to with that. But you have sodium sulfates, which are aqueous, that didn't fit, plus 2 aluminum nitrates, which are aqueous. Produces aluminum sulfate, which is a solid precipitate. So this is a double replacement reaction where it's precipitate, and that's why it's a reaction at all. Sodium nitrate. You get 6 of those. So that's our reaction, and it goes on to say if 345 milliliters of 1.25 molar aluminum nitrate is added to an excess of sodium sulfate, how many grams of aluminum sulfate will be produced? So that says a whole lot. And the first thing it's telling us is what is our liquid reactant, because you know you do all math with numbers from the liquid reactant. We figured that out because the sodium sulfate is the excess reactant. So we're not going to use that. If this one's an excess, then we know this one is our limiting reactant. Aluminum nitrate. And of course, this is all the information about the aluminum nitrate, which I've written here. So it tells us that it's 1.25 molar nitrate, that capital M, means moles of aluminum nitrate per liter solution. And it tells us that we have 345 milliliters, which is equal to 0.35 liters of that. So that'll let us cancel our liters. Apparently I canceled my chalk. Nope, that's not chalk. Okay. So I cancel my liters. But what is my put down the stuff I know the most about, the stuff that's the limiting reactant. Mole is grams of aluminum sulfate. So this, I wish I had another color, but grams of aluminum sulfate. So from moles of aluminum nitrate to moles of aluminum sulfate. Well, I can use the balanced chemical equation here to do that. So just pretend I'm continuing on, and I have a longer chalkboard, but the next step I'm just going to have to fit in here. So I want to cancel moles of aluminum nitrate. So this times here goes on. I want to cancel these moles of aluminum nitrate. And I want to get moles of aluminum sulfate here. So to do that, I just look at the balance equation. 2 grams of aluminum nitrate are used for 1 aluminum sulfate produced. So I just multiply by the mole-to-mole ratio from the balance equation. Cancel moles of aluminum nitrate. I've got aluminum sulfate. And what's my goal? My goal is grams of aluminum sulfate. I've got moles of it. I need grams of it. The way to convert between moles and grams is to use the molar mass. So hopefully you calculate the molar mass I have, and I'm going to copy it now. The molar mass of aluminum sulfate found to be 342.3 grams of aluminum sulfate per mole of aluminum, which I'm not going to try to fit on there again. So if I go through, I cancel my moles of aluminum sulfate. Alright, so if I go 1.25 times 0.345 divided by 2 times 342.3, then I get my answer, which I find to be 73.8 grams aluminum. And then I consider 3 significant figures, 3 here, 4 here, so I can keep 3, so that's correct. So that's problem number 3. Make sure you always use lots of information, only use the limited reactants numbers. Don't worry about the excess reactant. So hopefully you can see all that. And then we'll move on to number 4 says this. Aqueous sodium bromide silver nitrate will react to form solid silver bromide and nitrate. So another double replacement reaction, just like we talked about last week. We need to produce 100.0 grams of silver bromide. So of 2.5 silver nitrate must be added to the sodium bromide. And when you look at this balanced equation, I'm not going to write it on the board because all the coefficients are 1. So we don't have to worry. All of our mole-to-mole ratios will be 1. And in the paper, you can look at the practice problems. We want to make 100.0 grams of silver bromide. And we have molar silver nitrate. So we have to figure out how much nitrate we're going to use. Alright, so we've got grams of silver bromide. We will convert to liters of silver. So first thing we're going to do is convert to moles of silver bromide so we can use the mole-to-mole ratio to convert to silver nitrate. And the molar mass of silver bromide is, let's read my paper, 187.8 grams per mole. Alright, cancel out grams and get moles, so 1 mole of silver bromide is 187.8 grams. That cancels our. So now we have moles of silver bromide. We said that all of our coefficients are 1 in the balanced equation. So if we want to cancel out moles of silver bromide and get moles of silver nitrate, do it with that 1:1 ratio. Silver bromide cancels. Alright, so now I have moles of silver nitrate. And the problem also is the concentration of silver nitrate I'm going to use. I just need to know I just need to know how many liters to use. So, when I have concentration and molarity, we know that that is in moles per liter, right? So, if I cancel moles with it, I'm going to have to flip that over and say for every 1 liter of 2.5 molar silver bromide, there's 2.5 moles of the silver nitrate. Alright, so I just flip the molarity upside down because I'm using it as a conversion factor. So I can't count moles of silver nitrate, and I'll end up with moles of silver. And that's exactly what I need to know. How many liters should I measure out to mix in? So I take my calculator and do work divided by 27.8 times, obviously, divided by 2.5, and once we've done that, I come up with 0.21. I can keep two significant figures of that liters of 5 molar silver nitrate. So your complete answer, 4.1, two significant figures of 2.5 molar silver nitrate is needed to fully react with that. So always feel comfortable holding your conversion factors upside down. That's it's just like saying 1 foot equals 12 inches. But this is valid to write the conversion factor over 12 inches as it is to write 12 inches in 1 foot. You just flip it over depending on what you're converting, what units you need to cancel, which you end up with in the numerator. So very similar. When you sort of geometry, you can just flip. Alright. So that was number 4. We still have a long way to go. Number 5, a popular test for lead 2 ions in the contaminated drinking water is called the chloride test. This involves adding table salt, sodium chloride to water. Any 2 ions in the water will react with the chloride ions, forming a solid precipitate. And the reaction here, lead 2 ions plus 2 CDLs, give us lead chloride, which would be lead 2 chloride plus sodium ions. And it says measuring the mass precipitate in concentration of lead 2 ions in the water. An excess is added to 1.6 liters of water, and 25 grams of lead chloride are produced. A lot of lead in the water. With the molarity of the lead 2 in the water. So, what we're going to do here is, where should we start? So, we start with how much lead chloride is produced. What do we want to know in the end? What was the molarity of the lead ions? So, if you look at the balanced equation, you can see that what was the molarity of the lead? So the ratio, the coefficients for lead 2 ions and the lead chloride are both 1 to 1. So we don't have to worry there. We can just remember it's a 1 to 1 ratio. I'm not going to put the balanced equation on your paper. So we'll start here with 25.0 grams of lead 2 chloride. And I want to cancel out grams and get moles. So I'm going to use the molar mass of chloride, which hopefully you found. I'm going to cancel out grams. That is 278.2 grams of lead chloride for every 1 liter. So now I have moles of lead chloride, but I want to know about lead 2 ions. So I'm going to cancel out by using that 1 to 1 ratio in the balanced equation. I'm going to cancel out moles of lead chloride, and I'm going to try to get moles of lead 2 ions. So 1 to 1 ratio in the balanced equation. Then what do I I want to know the molarity of the 2 ions of water. So molarity is that solute per liters of total solution. How much water did I test? It looks like 1.6 liters of water. So that goes in the denominator. 1.6 water. And when I do 20 divided by that, I can keep 2 significant figures because of the 1.6. So I get this 0.056 molar lead 2 ions. And that's my molarity of the lead ions in the water. You can follow, even though I had to jump on there, can't fit everything. So let's see, we're on number 6. All right, number 6 says, if a solution is made by mixing 50 moles of KOH, which is potassium hydroxide, into 3.4 kilograms of water, what is the solution's molality? So just get in your mind, think about it before you start writing. Molality, moles of solute, kilograms of solvent. If you're using both this module, you really want to think it through each time just to be careful. Okay, so we want molality, moles of solute, with a solute here is KOH, potassium hydroxide, and luckily it already gives us, we don't even have to convert, so we'll start there. 50.0 moles of KOH. So now all I have to do is worry about kilograms of solvent in the denominator. And it just gives that too. It says 3.4 kilograms of water. Right, so that's pretty simple. Moles of solute per kilograms of solvent. Type it into your calculator. You keep 2 significant figures because of this. And you get 15 moles per kilogram, which is molality, little m. 15 molal KOH. 15 molal KOH. That's number 7. I can manage to do one more without erasing. Number 7 says, if a solution is made by mixing 35.0 grams of bromide with 657 grams of water, what is the molality? So this is only like one more little step beyond number 6 to give you grams, so we'll have to convert grams to moles. So let's here, our solute is calcium bromide. We start with 35.0 grams of calcium bromide. All right, so to convert that to know the mass from the periodic table, so add up 1 calcium, 2 bromine, and I found the molar mass to be 199.9 grams per mole for calcium bromide. So now I've canceled. I've got moles of my solute in the numerator. I just need kilograms of solvent in the denominator. So just pretend like we're continuing along on that line, even though I don't have space on the chalkboard. And it says that we had 657 grams of water. We know we divide by kilograms of solvent, so we'll convert that from 657 grams to 657 kilograms of water. Type this all into the calculator, and I found that I can keep 3 significant figures. 0.266 mole calcium bromide. Okay, so that's number 7. 0.266 mole calcium bromide. Okay. Number 8. If you want to lower water's freezing point by 15 degrees Celsius by adding sodium chloride, what must the molality of the salt solution be? Okay, so when we're doing colligative properties, like compression and boiling elevation, we use this equation. Let's see, times the constant. Okay, so we would lower the freezing point by 15 degrees, so the change in temperature is 15. That's going to be negative 15. It's not 0.0, is it? No. Okay. So we're using sodium chloride. We need to use I for sodium chloride. Well, NaCl is split into one Na plus ion and one Cl minus ion, so I is going to be 2. So negative in the equation 2 times the gas per water, which is 0.86 degrees Celsius per molality. And then we're just going to solve for the molality that we need. That's our unknown. So if I take my calculator, I take 15 divided by 2, and then divide that by 1.86. I find the answer to be, I keep 2 significant figures, so 4.0, and of course Celsius cancels out. I'm just left with molality as my unit, and I get 4.0 NaCl. You know from the first video is an entirely concentration at I don't know if you can get salt water like that at really, really cold temperatures. It's a sketchy problem. But NaCl doesn't really change significantly over temperatures like potassium chloride does, so maybe. So that was number 8. I wonder if I can find. I'll try. Alright. So, number 9 will be below the line. It says, what the freezing of a solution made by mixing 5.0 grams of NH3, which is ammonia, with 350.0 grams of water, freezing from water. So, we need molality first. It doesn't give us the molality, it just tells us how many grams are mixed in. So to find molality, remember moles of solvent, kilograms of solvent. So it tells us we have 35.0 grams of ammonia, and we need to convert that to moles, of course. So we want to cancel out grams, we need to get moles of NH3. The molar mass of NH3 you get from your adding up on your periodic table, 17.0 grams. So we can find that this solution, 3 significant figures, is 2.06 mole ammonia. So I'll put that in a little circle. 2.06 mole ammonia. So now I know molality. I know my solute is ammonia. So to plug in an I, what should I do? So this is a little bit tricky. To find out for ionics, you just think, well, how many ions does it split into? But when H3 dissolves, is it going to split up into N's and H's? Well, no. And non-metal, H is a non-metal. So this is a covalent compound. That's always one covalent compounds. They don't ionize because they're not ionic. They stick together. I is always 1 because it's going to form one particle for each ammonia molecule. So I is 1. So then let's plug in what's my goal here. Freezing point. Okay, so delta T is my goal. So when I write the equation, I have negative there. I is 1 because this thing is covalent. Times K of water, which is 1.8 degrees Celsius per molal. And then molality was 2.06. My little ones there. And I find the freezing point temperature to be, where am I? Oh man, I wrote that wrong. Oh my, how embarrassing. Alright, backtrack. Can't find molality. Space here. So now I found moles of ammonia, but to find molality, of course, I have to divide by how much water I have. So let's just that. Let's see. 350 grams of water. So I have to divide by kilograms of water. So that's going to be 0.350 kilograms of water. And so then I put this in my calculator, and I find the molality, which is 5.88 molal ammonia. Alright, so after that, everything's basically the same. My delta T will be -1 for I because it's covalent times the constant times this molality, which is actually correct, I hope. Let me know if I make any more mistakes. It's getting late at night. And so I do 1 times 1.6 times 7. I find the change in temperature to be, what is it? -10.9. I still keep 3 significant figures. -10.9 degrees Celsius. Remember, that's not good enough for your final answer. You have to say the freezing point is the normal freezing point, 0, plus this -10.9 degrees Celsius, gives a freezing point when we dissolve ammonia in. The new freezing point will be -10.9 degrees Celsius. But you can't just report delta T in the final freezing point, because you have to take into account the original freezing point, which basically is water. So you end up basically with the same thing. So that last step, which I can't fit there, you end up with freezing point equals -10.9 degrees Celsius. Because the freezing point of water is 0, and the change is just -10.9. So number 9, now I just need to do number 10 and we're on. So number 10 is what is the solution. So the boiling point in temperature is going to be I, not negative I, because the boiling point gets bigger as you dissolve solutes. Times the constant for boiling, not freezing, constant, still based on the solvent, which in this case is water, and that times the molality. Boiling point of a solution made of 100.0 grams of zinc chloride with 750 grams of water, and it gives you the boiling constant for water. So we have to find the molality of the zinc chloride portion. So it tells us alright, so we convert our grams of zinc chloride to moles. Molar mass of zinc chloride is 136.4 grams per mole. That cancels grams of zinc chloride. Now I have moles of zinc chloride. Molality is the solute divided by kilograms of the solvent. So a multiply sign there and divide it by kilograms of the solvent, which is water. So 150 grams, which is 0.750 kilograms of water. If I do 100 divided by 136.4 divided by 0.750, molality to be, and I keep 4 over. Oh, it sure is. So I keep figures. I get 0.975 molal zinc chloride. Right, the NCl2. I'm just out of room. Okay, now I've got the molality of zinc chloride. Now I want to find what the change in boil is. So delta T. Okay, so I for zinc chloride. How many pieces will ZnCl2 split into? It is ionic, we'll split into 1 zinc cation, fluorine anions, so 3 total pieces. So 3. Kb for is 0. Oops. Hello. Okay. Kb for water is 0.12 degrees Celsius per mole. And the molality is, if I can fit it. Alright, our little m pencil. Then I type 3 times 0.152, no, 0.512 times 0.955. Yeah, I'm really tired, guys. You can type it into your calculator better than I can say it, apparently. And I find in degrees Celsius is going to be 1.50 Celsius. I can only keep 3 because of my boil constant. So then, that last step becomes more important here because the boiling point of water is 100. So boiling point BP is going to be 100 degrees. That boiling point of water plus 1.50 degrees change in temperature. So we 101 degrees Celsius, if I can. And significant figures for the boiling point to the 10th for us, we'll keep to this place in our answer. So 101 degrees Celsius would be the boiling point of that zinc solution of that molality. So you dissolve chloride in some water, the boiling point goes up, and instead of 100, it will be 101.5 degrees Celsius. So that's all the practice problems. I promised you by bedtime tonight to send out an email. You guys can keep working, and so next Sunday, but please do my work.